In this lecture we shall define when a mapping is a bijection, and we shall define the inverse mapping associated with a bijection. Let's consider the three possible situations for the elements of the codomain of a mapping. An element of the codomain of a mapping may have two incoming arrows or more, exactly one incoming arrow, or no incoming arrows at all. A bijection is a mapping that satisfies the property that for every element in the codomain, there is exactly one element in the domain that maps to it. So, by requiring that a mapping is a bijection, we exclude the situation that an element of the codomain may have two or more incoming arrows, and we exclude the situation that there are no incoming arrows at all. A bijection is sometimes referred to as a bijective mapping. Let's consider a couple of examples. First, let's consider the mapping f from real numbers to real numbers, such that f of x is x squared minus 1 for all real numbers x. This mapping is not a bijection. To understand why, let's have a look at its graph. The mapping f fails the requirements for being bijective in many ways. For instance, both minus 2 squared minus 1 and 2 squared minus 1 equal 3. So 3 is an element in the codomain of this mapping with two incoming arrows. And also, since there do not exist real numbers x such that x squared minus 1 is less than minus 1, real numbers less than minus 1 do not have any incoming arrows. Let us stress here that to refute that f is bijective, it suffices to produce just one example of an element of the codomain to which f either maps two or more, or no elements of its domain. That we have mentioned here two reasons is just for illustration purposes. If we restrict the domain of f to comprise only the non-negative real numbers and restrict the range of f to comprise all real numbers greater or equal minus 1, then we eliminate all counterexamples against bijectivity. Indeed, as is also suggested by the graph, f then is a bijection. For every real number y greater or equal minus 1, there is exactly one non-negative real number x, such that x squared minus 1 equals y. For another example of a bijection, consider the mapping g from integers to even integers, defined for all integers x by g of x equals 2 times x. Then g is a bijection, since clearly, for every even integer y, there is a unique integer x such that y equals 2 times x. We now wish to characterize bijectivity more precisely with a formula of predicate logic. Note that requiring that there are no elements in the codomain with no incoming arrows is the same as requiring that the mapping is surjective. And requiring that there are no elements in the codomain with two or more incoming arrows is requiring that the mapping is injective. So we can formalize the property of being bijective as the conjunction of being surjective and injective. The resulting formula is essentially the property of bijection, but it is convenient to present it a bit more concisely, using the special variant of unique existence that we have also used when defining the property of mapping. Note that the second conjunct expresses that for all y there is at least one x such that f of x equals y, and that the first conjunct expresses that there cannot be more than one x that is mapped by f to the same thing. We can incorporate the first conjunct into the second simply by requiring unique existence of the element x in A such that f of x equals y. Thus, we obtain the formula that corresponds to the property of bijection. A mapping f is a bijection if and only if, for every element y in its codomain, there is a unique element x in its domain such that f of x equals y. Suppose that f is a mapping from A to B, then we can define a relation R from B to A, stating that for all y in B and x in A, y is related to x by R if and only if f of x is equal to y. Note that we obtain the arrow graph of R from the arrow graph of f by reversing the arrows. Now we may observe that if f is a bijection, then according to the property of bijection, it satisfies the formula for all y in B there exists a unique x in A such that f of x equals y. Using the definition of R, which states that the predicate f of x equals y is equivalent to the predicate y rx, we may replace f of x equals y by y rx. We then get the formula for R is a mapping. The upshot of this is that whenever f from A to B is a bijection, then we get a mapping from B to A simply by reversing its arrows. This mapping is called the inverse of f. We shall now state the definition of the inverse of a bijection f from A to B again, introducing special notation for it. The inverse of a bijection f from A to B is a mapping from B to A, denoted by f with a superscript -1, and defined for all x in A and y in B by the inverse of f applied to y is equal to x, if and only if f applied to x is equal to y. We illustrate the notion of inverse by considering the two example bijections we have encountered earlier in this lecture. First, consider the bijection from non-negative reals to real numbers greater or equal -1, defined by f of x is x squared minus 1. The inverse of this mapping is the unique mapping that associates with every real number y greater or equal -1 the square root of y plus 1. Next, consider the bijection g from integers to even integers such that g of x is 2 times x. The inverse of g is the unique mapping from even integers to integers that associates a half y with every even integer y. Returning to the definition of inverse mapping, recall that it requires for all x in the domain of f and for all y in the codomain of f that the inverse of f applied to y is equal to x if and only if f applied to x is equal to y. So if we know that the inverse of f applied to y is equal to x, then we may conclude that f of x is equal to y, and vice versa. The property of inverse will express exactly this. It states that the predicate inverse of f applied to y equals x is equivalent to the predicate f applied to x equals y. It can hence be used in two directions: to conclude that f applied to x equals y from the inverse of f applied to y equals x, and to conclude that the inverse of f applied to y equals x from f applied to x equals y. To summarize, a bijection is a mapping satisfying the property that for every element in its codomain, there is exactly one element in its domain that maps to it. And with every bijection, we can associate a well-defined mapping in the other direction. It's called the inverse mapping, which is incidentally also a bijection. This concludes our lecture on bijections and inverses.